July 1st, 2025. An MIT-linked telescope sweeps the Chilean sky as usual until its sensors catch something that should be impossible. Hurtling through the solar system at over 130,000 miles per hour, 3E/Atlas isn't bound by the sun's gravity, and its path makes no natural sense. The third ever interstellar visitor, largest of its kind, and already rewriting the rules of science, its speed, size, and strange chemistry defy every comet model on the books. Now, fresh data reveals unexplained forces steering its journey, igniting fierce debate. Is this a cosmic fluke, or proof that we're missing something profound? Before the headlines called it a once-in-history discovery, someone had to spot it first. How did scientists catch an intruder so bizarre, and what tipped them off? A faint blip appeared on the Atlas control room's monitor just after midnight, flagged by the automatic survey pipeline as a possible fast mover. Ana Morales, the night technician on duty, leaned in. The system's algorithm had caught plenty of asteroids before, but this one was different. Its trail was sharper, its motion almost surgical. The magnitude reading hovered near 18, barely above the noise floor. The software's alert flashed. Velocity estimate, off the charts. Morales hesitated, then ran the raw frames again. There it was. 3 exposures, each separated by minutes. Each showing the object slicing through the starfield at an angle that made no sense for anything local. Protocol demanded caution. She checked the night's logs for glitches, then pinged the senior astronomer on call. Within minutes, the team gathered around the main screen, watching the data stack in real time. Someone pulled up the Minor Planet Center database. No match. The immediate fear, a near-Earth object on a dangerous trajectory. But the numbers didn't line up. The calculated speed, over 57 kilometers per second, simply didn't fit any known solar system body. As the team double-checked the astrometry, a second alert came in from the Zwicky Transient Facility in California. Their archive, dated June 14th, showed faint traces of the same object, already moving too fast and too straight to be anything but unbound. The room shifted from nervous energy to excitement. Cross-referencing the Atlas and ZTF data, the trajectory became clear. This was a visitor from beyond the sun's reach, on a hyperbolic path that would never close. Morales submitted the initial discovery report before dawn. Within hours, observatories across the globe began scanning the coordinates, confirming what the Chile control room had first glimpsed. A cosmic intruder, brighter and faster than anything in recent memory. The official designation came quickly. 3I/Atlas, the third interstellar object ever spotted. For a moment, the control room was silent, everyone aware they'd just witnessed the start of a story that would ripple through science for years to come. Now, consider the numbers that turned a faint Chilean blip into a scientific sensation. 3I/Atlas does not simply wander through the solar system, it tears through it on a path no native comet or asteroid could follow. Its measured speed, just over 58 kilometers per second relative to the sun, is not a matter of rounding error or observational fluke. That velocity is nearly 3 times faster than the average main belt asteroid, and far beyond the escape velocity of any solar system planet. No gravitational tug from the sun or planets could ever slow it down enough to keep it here. Once it passes, it is gone forever, an unbound traveler. The shape of its trajectory tells the same story. Astronomers plot orbits using a number called eccentricity. For nearly every object bound to the sun, from Mercury to the outermost comets, eccentricity falls between 0 and 1, ellipses and stretched ovals, always curving back. 3I/Atlas, by contrast, has an eccentricity of about 6.08. That's not just hyperbolic, it's a mathematical declaration of freedom. The path is so open, so close to a straight line, that it could only have started in deep interstellar space. The angle of approach adds another twist. 3I/Atlas sweeps in on a retrograde orbit, tilted roughly 175 degrees to the plane of the planets. Instead of following the orderly traffic of the solar system, it barrels in almost head-on, crossing the ecliptic backwards. This retrograde high-inclination path is a fingerprint of an object born far outside the Sun's domain. Confirmation required more than a single observatory. Within days, teams from Hawaii, California, and Europe submitted their own astrometric measurements. Each dataset, when plugged into standard orbital models, returned the same answer: a hyperbolic excess velocity, an orbit that never closes, and a trajectory that points to origins well beyond the Oort cloud. The Minor Planet Center and JPL Horizons Ephemerides both converged on the same solution. There was no plausible way to fit the data with any bound orbit. The evidence was not just compelling, it was mathematically inescapable. This is only the third time in history such a verdict has been rendered. Oumuamua in 2017, 2I/Borisov in 2019, and now 3I/Atlas, all confirmed by their speed, their openness, and their refusal to bend to the sun's pull. But Atlas stands apart for its sheer velocity and the sharpness of its trajectory. Across every model, every recalculation, the proof remains. This is an interstellar visitor, a one-time cosmic encounter, and a challenge to everything we thought we knew about what drifts between the stars. Size in the world of astronomy is always relative. For 3I/Atlas, every estimate stretches the imagination. Early Hubble Space Telescope imaging suggested a nucleus somewhere between 320 meters and 5.6 kilometers across, a range that alone would place it among the largest interstellar objects ever observed. Yet some ground-based teams, using adaptive optics and deep stacking from observatories like Gemini South and the Gran Telescopio Canarias, reported upper bounds as high as 11 kilometers. One provocative analysis, assuming a perfectly solid, inactive core, argued for a diameter approaching 20 kilometers. Even at the lowest end, 3I/Atlas dwarfs its predecessors. For reference, Oumuamua was barely 400 meters long, while Borisov measured close to a kilometer. If these numbers hold, this is comfortably the largest interstellar wanderer humanity has ever glimpsed. But sheer size is only the beginning. 3I/Atlas is faint by human standards, discovery magnitude near 14, requiring the full power of professional-grade telescopes to see. That faintness is deceptive. The object's brightness is not simply a reflection of its core, but the result of a vast, expanding shroud. Surrounding the nucleus, a coma, an envelope of gas and dust, stretches to immense proportions. Observations in July 2025 with the Gran Telescopio Canarias measured this cloud at 26,400 kilometers by 24,700 kilometers. That is nearly twice the diameter of Earth. In near-infrared, NASA's SphereX mission caught something even more dramatic. A carbon dioxide halo extending over 340,000 kilometers from the core, nearly the distance from the Earth to the Moon. The activity does not stop there. By late August, the dust tail trailed more than 56,000 kilometers into the void, a sign of intense and ongoing ejection. Each layer, core, coma, halo, tail, adds scale upon scale until the true extent of Atlas becomes almost impossible to comprehend. Every instrument from the Hubble's ultraviolet and optical eyes to the ground-based giants in Chile and Spain contributed a piece of the puzzle. The Vera Rubin Observatory, designed to scan the entire southern sky, flagged Atlas repeatedly, tracking the evolution of its envelope in near real time. Such activity is not typical for interstellar objects. Borisov, the only previous interstellar comet, displayed a classic coma and tail, but never approached these dimensions. Oumuamua, by contrast, had no visible coma at all. Atlas, in every respect, is larger, brighter, and more active than anything seen before from beyond the sun's reach. Its coma and halo are not just big, they are colossal. challenging the upper limits of what astronomers thought possible for a visitor from another star system. In many ways, we are peering through a keyhole at a cosmic giant, struggling to measure it before it vanishes forever. The instruments brought to bear, HST, Spherix, GTC, Gemini, and Rubin, represent the full arsenal of modern astronomy, each straining to resolve the true nature of this interstellar colossus. The sheer scale and activity of 3Y/Atlas have left scientists astonished, forcing a rethinking of what interstellar debris can be. All of this, before even considering the chemistry that waits beneath the surface. The journey of 3D/Dallas through the inner solar system is a race against time, each planetary flyby offering only a fleeting window for observation. The countdown began in earnest as astronomers mapped its projected path, an arc that would bring it startlingly close to Mars before sweeping past the Sun and into deeper space. On October 3, 2025, 3D/Atlas will pass within 0.21 astronomical units of Mars, about 31 million kilometers, or roughly 80 times the distance from Earth to the Moon. For planetary scientists, this encounter is a rare alignment. Mars orbiters, like NASA's Mars Reconnaissance Orbiter, are poised to capture images and spectra from a vantage point no Earth-based telescope can match. The geometry is nearly ideal. The comet's coma and tail will be backlit by the Sun, maximizing the contrast for ultraviolet and infrared instruments. Every minute of data could reveal new secrets about the chemistry and dust escaping from this interstellar visitor. But the Mars flyby is only the first act. Less than 4 weeks later, on October 29th, 3D/Atlas will reach perihelion, its closest approach to the Sun, at just under 1.4 astronomical units. This is inside the orbit of Mars, where solar heating peaks and cometary activity tends to reach its most dramatic crescendo. Astronomers expect the coma and tails to expand rapidly, possibly revealing jets, fragmentation events, or chemical transitions never before seen in an object from another star. The intensity of sunlight at this distance will drive volatile ices to sublimate furiously, feeding the already colossal halo of gas and dust. Instruments aboard the James Webb Space Telescope and the Hubble Space Telescope are scheduled for time-critical observations, aiming to dissect the evolving chemistry as the comet responds to solar energy. Just days after perihelion, on November 3rd, Atlas will pass near Venus. Though it won't approach closely enough for Venus-based observation, the geometry provides a valuable change in viewing angle. This shift helps astronomers disentangle the three-dimensional structure of the coma and tail, crucial for modeling how sunlight sculpts the dust and gas as the comet speeds away from the Sun. For Earth-based observers, patience is required. The closest approach to our planet comes on December 19th at a distance of about 1.83 astronomical units, 270 million kilometers. Even at its brightest, Atlas remains faint, hovering around magnitude 14. Only the world's largest telescopes, Gemini South in Chile, the Very Large Telescope in Paranal, and the Gran Telescopio Canarias, will be able to track it in detail. The Vera Rubin Observatory, with its sweeping all-sky coverage, will monitor the comet's outbound journey, searching for late-stage outbursts or fading fragments as it retreats into the darkness. Throughout this passage, the window for high-quality data is narrow and unforgiving. Early in its approach, the comet hugs the glare of the Sun, making detection a challenge, even for seasoned professionals. Only as it rounds the Sun and climbs higher in the night sky does it become accessible to Southern Hemisphere observatories. By late September and into October, the angle between the comet and the Sun, known as elongation, improves, allowing longer exposures and more precise measurements. December brings the best separation, but also the fastest outbound motion as Atlas accelerates toward the edge of the solar system. Every campaign is a logistical puzzle. Teams coordinate across continents, scheduling precious hours on telescopes, synchronizing with space-based assets, and racing to capture spectra, images, and polarization data before the comet slips away. The urgency is real. Miss a night, and a crucial phase of activity could be lost forever. For the scientists watching 3I/Atlas, each date on the calendar is a deadline, each flyby a singular chance to observe a phenomenon that may not repeat for decades or centuries. The clock is ticking, and the comet will not wait. Spectroscopists from MIT and around the world turn their attention to 3I/Atlas, hoping to decipher the chemistry hidden in its faint glow. Using the James Webb Space Telescope's NIR SPEC instrument, the team obtained some of the most detailed spectra ever recorded for an interstellar object. The results were immediately baffling. Instead of the familiar fingerprint of water vapor, by far the dominant volatile in solar system comets, these spectra were dominated by carbon dioxide. The ratio was not close. For every molecule of water detected, there were about 8 molecules of carbon dioxide. That is an 8-to-1 ratio, so far outside the norm that it forced a complete rethinking of how such an object could form. In comets from our own solar system, water ice typically outnumbers carbon dioxide by 10-to-1, sometimes more. Even among the coldest and most distant bodies, a carbon dioxide-rich composition like this is almost unheard of. Independent confirmation came from SphereX, NASA's infrared all-sky surveyor, which mapped the carbon dioxide halo stretching over 340,000 kilometers from the nucleus. The sheer abundance of carbon dioxide, measured across multiple instruments and epochs, remained consistent as the object approached the Sun. Laboratory models of ice formation at extremely low temperatures, below -240 degrees Fahrenheit, can, in theory, trap extra carbon dioxide, but not at these levels. The chemistry of 3I/Atlas is not just unusual. It is extreme, and it does not match any known family of solar system comets, centaurs, or trans-Neptunian objects. If the gas composition was a surprise, the metallic signature was something else entirely. High-resolution spectra from the Very Large Telescope in Chile revealed bright emission lines of neutral nickel, an unmistakable atomic marker. But the expected companion, iron, was almost entirely absent. In the solar system, nickel and iron travel together, forged in the same supernovae, locked together in meteorites and planetary cores. Here, nickel appears alone, at about 20% of the strength seen in typical comet spectra, while iron is missing or below detection limits. This is not a minor quirk. It is a chemical fingerprint that defies standard models of planetary building blocks. Theorists race to explain how such a signature could arise. Some propose that cosmic rays or long-term space weathering might selectively erode iron from the surface, leaving nickel behind. Others invoke the possibility of a differentiated parent body, one that melted and separated, allowing nickel-rich layers to reach the surface. Laboratory experiments are now underway to test whether nickel can be released from icy grains more efficiently than iron under intense ultraviolet light, but so far, no mechanism fits all the data. The combination of a carbon dioxide-dominated coma and nickel without iron sets 3I/Atlas apart from every comet cataloged to date. Each spectrum, each emission line, adds to the puzzle. The chemistry is not just a curiosity. It is a challenge to the very assumptions that underlie our understanding of planetary formation, both here and in distant star systems. For the scientists parsing these signals, 3I/Atlas is not just an interstellar wanderer. It is a messenger carrying secrets no one expected to find. Color, in the world of comets, is more than a visual flourish. It's a clue to chemistry, history, and cosmic birthplace. As 3I/Atlas approached the Sun, astronomers began to notice something odd. Early images, taken at the edge of the solar system, hinted at a muted reddish tone, typical for dormant dust-shrouded bodies wandering far from stellar warmth. But as the comet's activity ramped up, reports from Gemini South and the Very Large Telescope described a striking transformation. The coma, once tinged with the deep rust of cosmic weathering, began to glow with a greenish cast. This shift, while subtle to the naked eye, sent a ripple through professional circles. Cometary greens often signal the presence of excited molecules, cyanogen, diatomic carbon, or even atomic oxygen, set aglow by the sun's ultraviolet light. Yet for Atlas, the underlying chemistry is anything but standard. The overwhelming abundance of carbon dioxide, paired with a scarcity of water vapor, means that as sunlight penetrates deeper, it stirs up a different mix of gases and dust grains than in any comet seen before. Some researchers point to the excitation of carbon dioxide and rare nickel emissions as possible contributors to the evolving hue. But the full recipe remains elusive. Polarimetric studies add another layer. Light scattered by Atlas's dust matches the pattern seen in distant, icy objects beyond Neptune. Bodies rich in dark carbon compounds, porous and fragile, shaped by eons in the cold outskirts of the galaxy. This behavior, rare among solar system comets, hints at a nucleus built from materials more ancient and less processed than anything orbiting the Sun. The grains themselves seem unusually fluffy, amplifying their response to solar radiation and possibly helping to drive the comet's dramatic activity. Galactic context sharpens the mystery. Atlas's trajectory and chemistry have led some astronomers to propose an origin in the Milky Way's thick disk, a population of stars and debris, older than Earth by billions of years, forged in a different era of galactic history. If true, the comet's color evolution might be a fingerprint of that ancient heritage. Dust grains and ices, shaped in a metal-poor environment, now reacting in unfamiliar ways as they are exposed to sunlight for the first time in eons. Still, caution tempers every claim. As of late 2025, no peer-reviewed time series photometry confirms the precise timing or magnitude of the red-to-green transition. Visual reports and informal campaign summaries suggest the phenomenon is real, but the data remain qualitative. Teams from MIT, NASA, and the European Southern Observatory are racing to release calibrated color indices, hoping to tie these observed changes to the comet's outbursts and, perhaps, to its galactic birthplace. For now, the color of Atlas stands as a tantalizing signal, one that could connect the dust in our telescopes to the oldest building blocks of the Milky Way. Astrometric data from observatories worldwide began pouring in as soon as 3D/Atlas was identified. Each new measurement, right ascension, declination, timestamp to the second, became a data point in a growing puzzle. Orbit modelers at MIT, JPL, and the Minor Planet Center worked in parallel, running the numbers through gravity-only simulations. By mid-August, a pattern surfaced. The observed positions of Atlas were drifting, subtly at first, then unmistakably, away from the path dictated by gravity alone. The residuals, those tiny discrepancies between predicted and measured positions, grew steadily with each night's data. By September, the divergence exceeded a full arc-second, far beyond the error bars of even the most crowded star field. To account for this, teams introduced non-gravitational parameters into their orbital fits. The classical Marsden model, which assumes water ice sublimation as the main driver, could not explain the magnitude or timing of the deviation. Instead, the best fit solution required both a strong radial acceleration, A1, measured at roughly 4.1 times 10 to the -7 astronomical units per day squared, and a significant transverse component, A2, near 2.3 times 10 to the -7 astronomical units per day squared. These values are not only large, but statistically robust, with uncertainties well below the threshold for chance. For context, 1I/Oumuamua's unexplained acceleration was smaller and only apparent after perihelion. 2I/Borisov, a more conventional comet, showed nothing like this at similar distances. What truly unsettled the analysts was the timing. The acceleration in Atlas's path appeared before any major outgassing event at heliocentric distances where solar heating is too weak to drive strong activity. Even after incorporating carbon dioxide-driven models, the amplitude remained extreme. Some proposed that a porous, low-density core could amplify the effect of solar radiation pressure, but the mass loss rates implied by the observed brightness did not add up. Others suggested episodic fragmentation, bursts of material jetting off in random directions. Yet, the acceleration persisted even in the absence of obvious dust ejection. Every modeling group, using different software and weighting schemes, arrived at the same conclusion. The path of 3I/Atlas cannot be fit by gravity alone. The statistical tests, F-scores, Bayesian information criteria, all decisively favored the inclusion of non-gravitational terms. Yet the physical origin of these forces remains a matter of debate. Are we seeing the signature of exotic chemistry, a nucleus on the verge of disintegration, or something stranger? For now, the numbers themselves are irrefutable. The orbit of Atlas is being pushed by an invisible hand, and the search for its source is just beginning. Every theory on the table is being tested against the riddle of 3/Atlas. Some researchers, working from first principles, trace the comet's wild path and outsized acceleration to the physics of a fragile, low-density body. In this view, Atlas might be a cosmic snowflake, an object so porous and lightweight that sunlight itself pushes it off course, amplifying every jet and fragment. Outgassing from deep inside, especially if driven by carbon dioxide instead of water, could create unpredictable thrusts. Each burst would nudge the orbit, explaining some, but not all, of the measured anomalies. Yet the numbers strain even these explanations. The magnitude and timing of the acceleration, detected while Atlas was still far from the Sun, have led some to propose more exotic answers. One possibility: interactions with the interstellar medium, a thin soup of gas and magnetic fields that fills the galaxy. If Atlas carries an unusually large surface area or an extended cloud of charged dust, it could experience a drag or pressure unlike anything seen in solar system comets. But no existing models predict the scale of the effect observed here. A more radical hypothesis draws on the precedent of Oumuamua, whose unexplained acceleration in 2017 sparked a wave of debate. Professor Lowe, a prominent and sometimes controversial voice, argues that Atlas's size, brightness, and orbital deviations demand consideration of artificial origins. Could this be a solar sail, an engineered sheet propelled by sunlight crossing the void between stars? The idea is provocative, echoing the debates that followed Oumuamua's passage, but now amplified by Atlas's far greater mass and activity. Critics point out that the observed coma and tail that are hallmarks of natural comets, not spacecraft. Lowe counters that the data do not fit any simple category, insisting, if it's not a rock and it's not a snowball, what else is left? Comparisons sharpen the stakes. Oumuamua was small, dark, and silent. No visible coma, no dust, only a mysterious push as it sped away. Borisov, by contrast, was a textbook comet, rich in water and behaving as expected. Atlas towers over both, larger, more active, chemically bizarre, and with even bigger orbital deviations. Each interstellar visitor then has rewritten expectations. But Atlas is forcing astronomers to redraw the boundaries of what is possible. As new data arrive from every corner of the globe, the debate grows louder. Natural or artificial, physics or artifact, comet or something entirely new. The only certainty, 3I/Atlas refuses to fit the rules laid down by its predecessors. Around the world, a network of telescopes and spacecraft sprang into action as soon as 3I/Atlas was confirmed. The James Webb Space Telescope, high above Earth's atmosphere, targeted the comet with its infrared spectrograph, searching for volatile gases and mapping the structure of its coma. Hubble, with its ultraviolet and optical instruments, captured the faint shimmer of metals and rare molecules in the expanding halo. On the ground, teams at Gemini South, the Very Large Telescope, and the Gran Telescopio Canarias raced to secure observing time, each aiming to catch different wavelengths and dust signatures as Atlas swept across the southern sky. Mars orbiters, including NASA's Mars Reconnaissance Orbiter, were retasked for a rare opportunity: observing the comet from a vantage point inside the solar system as it passed near Mars in early October. This unique geometry allowed scientists to image the backlit coma and tail, probing their depth and structure with unprecedented clarity. Meanwhile, the Vera C. Rubin Observatory, still in early commissioning, shifted its wide-field survey to track Atlas nightly, providing a continuous record of its changing brightness and position. Each instrument contributed a piece of the puzzle. JWST's infrared data revealed the dominance of carbon dioxide, while Hubble's ultraviolet snapshots traced the spread of metals. Ground-based teams measured the polarization of scattered light, uncovering clues about the dust's size and composition. Coordination was relentless. International calls, shared schedules, and real-time data exchanges ensured that no moment of activity went unrecorded. The campaign was not just a display of technological power, but a testament to scientific teamwork, as dozens of observatories worked in concert to capture every fleeting detail of this interstellar visitor. The arrival of 3A/Atlas has forced astronomers to reckon with the limits of their own preparedness. Each new interstellar object, from Oumuamua to Borisov, and now Atlas, has arrived unannounced, offering only a brief window for observation before vanishing into the cosmic dark. The lesson is clear. The next visitor could appear at any time, and the current infrastructure is only just keeping pace. In response, the Vera C. Rubin Observatory has shifted from passive survey to active sentinel. Its nightly scans now prioritize rapid detection of fast movers, objects with the telltale hyperbolic signatures that hint at interstellar origin. The goal is not merely to catch the next Atlas, but to trigger a global alert within hours, mobilizing telescopes and instruments across continents and in orbit. The hope is that, with faster identification, more of the object's passage can be captured, from first approach to final retreat. But vigilance is not enough. The scientific community is debating the need for a rapid response probe, an automated spacecraft ready to launch at a moment's notice, capable of intercepting the next interstellar intruder. Feasibility studies circulate through aerospace boardrooms, their memos full of urgency and frustration. The clock is always ticking too fast for current technology, but each new event adds weight to the argument for building such a mission in advance, even if it waits years for its moment. For now, the legacy of Atlas is a heightened state of readiness. Survey teams refine their algorithms. Mission planners sketch blueprints for probes that might one day chase down a visitor from another star. The question is no longer whether another will come, but whether humanity will be ready to meet it when it does. On July 1st, 2025, the Atlas Survey Telescope in Chile detected 3A/Atlas, the third confirmed interstellar object, traveling at over 57 kilometers per second, too fast to ever return. Observations from the HST and ground-based telescopes revealed a nucleus, possibly up to 11 kilometers wide, surrounded by a coma stretching 26,400 kilometers, and a carbon dioxide halo over 340,000 kilometers across. Spectroscopy confirmed a rare carbon dioxide to water ratio of 8:1 and a puzzling nickel emission without iron. Despite coordinated global campaigns, 3A/Atlas's early non-gravitational acceleration remains unexplained, with leading theories ranging from internal fragmentation to unknown forces. The object's chemistry and dust properties suggest it formed in the Milky Way's thick disk, making it potentially billions of years older than Earth. Yet key questions about its true size, cause of acceleration, and ultimate origin remain unresolved. As 3A/Atlas exits the solar system, it challenges our models of comet behavior and planetary system diversity. The data collected mark a turning point in interstellar science, proving that the universe still holds surprises no model can yet fully explain.